So in the last lecture, we saw how to define the integral of a non-negative measurable function. And now we're moving into how to integrate a general real value function, okay? So if you recall what happens in PMATH 450 when you define the Lebesgue integral, okay? So you start with integrating the non-negative function, and then you say, well, if you have a real value function, you kind of divide it into the positive part minus the negative part, and you take their difference, okay? So that's essentially what we're going to do here. So all the construction you're going to see in this lecture is going to be really similar to what we did in the Lebesgue integral. So I'll just try to go through it fairly quickly, all right? So now here, let's start with our definition. So we want to make some definition. So let's fix some measurable space. Let's say x b mu is a measurable space, okay? And now I want to talk about the integration of a real value function, okay? So let's say f from x to the real value. So here f may now be non-negative. It can take negative value. Okay, so of course it needs to be measurable, otherwise I can't really say anything about that. All right, so let's call this function is integrable. So this is integrable. If the following happens, if I take the integral of the absolute value of f, okay, and d mu, then this absolute value, well, now is a non-negative function, so we already saw how to integrate non-negative function. So if this one is not equal, but is finite, so if less than positive infinity, then we say this function f is measurable, okay? So this is our definition. So this is essentially the same as how I define measurable function on the real line, okay? So now, so I want to define for measurable function, I can define is integral of this f, okay? So if f is measurable, let's define two functions, okay? The positive part and the negative part. So the f plus is the positive part, so let's take the maximum of f and 0. So if it's less than 0, let's just replace it by 0. Otherwise, take the f of x. The f minus is the maximum of the negative f and 0. So if f is negative, I take the negative of that negative value, which is positive. And otherwise, I just replace it by 0, okay? So you can see that these two are really positive functions, and it's the maximum of two measurable functions, okay? We saw a supremum of a countable collection of measurable functions measurable, and now we have two of them, so you can think about it as a supremum, so they're measurable as well. And another thing is that if you draw a picture, if you think about it, so I have some positive part and a negative part. The positive part, so it's like that, you replace it by 0, and the negative part is just the negative of this part, okay? So I may change the color, so you do the negative of that, and otherwise it's going to be equal to 0, okay? So based on this picture, and you can just do some easy exercise, you can convince yourself the following. So first of all, the function f is just the difference between these two non-negative functions, okay? So it's the f plus minus the f of minus. And moreover, the absolute value of f, well, what is absolute value is essentially taking either the f, or when f is negative, you take the negative of f. So it's essentially the sum of these two non-negative functions, okay? So that's very nice. And in particular, we can see that f plus and f minus are both bounded above by this function of f. Well, because it's bounded above by this absolute value of f, we know that the integral of non-negative functions, so these two are non-negative, and they're bounded above by this measurable absolute value of f, which has finite integral. So in particular, this integral of f plus d mu and the integral of f minus d mu, I should say f minus d mu, they're all bounded above by this integral of the absolute value of f, which is less than infinity, and we know they're non-negative. So in particular, I have two finite number, the integral of f plus and f minus, they're both finite, okay? So now let's define, let's kind of abuse the notation a little bit. So now I want to define the integral of a real value function f. So here I'm still using the same notation, but here I'm really making a new definition. So f can take a negative value. But I'm going to define it using the integral of some non-negative function. So let's do the integral of f plus, and let's do the integral of the f minus. Okay. So this is how we define this integral of any real value function. So here it's really making sense because these two integrals are both finite, so you're not taking a difference of to infinity. Okay, that will be not defined. Okay. All right. So now we have a definition of this integral. Okay. So I want to prove several nice property of this. Okay, so first of all, let's define the L1 space. Okay, so define the L1 space of mu is essentially all the integrable functions on X. Okay, so here f is integrable. And I can define, well, you probably already know from 450, so this space is almost like a norm vector space because you can put a norm, let's call this one norm. It's equals to the integral of its absolute value. So this is going to be almost like a norm, but there's only one slight problem is that in this one norm can be equal to 0, but f is non-zero. Okay, if integral of f is equal to 0, it just means f is 0 almost everywhere. So it can be non-zero somewhere. Okay, so in the next few videos, we're going to develop how we take a quotient of this L1 and we get a normed vector space. So that's quite a standard procedure. I'll leave it to the next video. Okay, but let's prove that this one norm defined just on this L1 space. It's not a norm, but it's almost like a norm. We call it a semi-norm or a pseudo-norm. Okay, so here is the proposition. So this L1 of mu is actually a vector space. And moreover, this one norm we just defined is actually not a norm, but a semi-norm. Okay, I know Ken's course note call it a pseudo-norm. They're the same thing. Okay, so what does it mean by a semi-norm? Is basically satisfy the following. So the one norm of the zero function is equal to 0. That's kind of trivial. The norm, if you want to scale it by some scalar, you can pull out the scalar and, well, pull out the absolute value of the scalar, and you do that, okay? And finally, it needs to satisfy this triangle inequality. So the one norm of f plus g is less than equals to f one norm plus g one norm, okay? So here we just, usually this is not a norm because the one norm can be 0, but f is non-zero. So let's just say, so here, add a remark. So here the f1 norm is equal to 0 if, and only if, so maybe let's just say this, f is equal to 0 almost everywhere mu, okay? So the non-zero is a null set, okay? So let's prove this fact. Okay, so to show it's a vector space, we basically just need to show it's closed under scalar multiplication and addition. Okay, so but as you can see, f is integrable if and only if its one norm is finite. So as long as we can show the one norm is a semi-norm, this L1 of mu is automatically a vector space. Okay, so let's just prove it's a semi-norm. Okay, so first of all, the one norm of 0 is equal to 0. That's just trivial. I'm not going to write it. If you do the one norm of a scalar, that's by definition the integral of the entire alpha absolute value d mu. And you can pull out the absolute value. So here, I can pull this alpha absolute value out because everything here is integrating of a non-negative function. Okay, we didn't really show the integral of integrable function is linear yet. Okay, it's easy exercise, but here we're not using any of that. Okay, so here is everything is positive. So alpha f is absolute value is positive, absolute value of f is positive. So we're good. Okay, we can pull out this alpha. All right, but on the right-hand side, this is just the alpha times the F1 norm. So we proved this linear scalar. And the other one is also kind of trivial. So if you just write out the definition, so this is the integral of the absolute value of f plus g. You know the absolute value satisfies the triangle inequality, so you can break it into the absolute value of f plus absolute value of g. And again, we're doing integral of non-negative functions here. So this is, we show the integral of non-negative functions linear. So I can break this integral into two parts. And that's just the F1 norm plus G1 norm, okay? And finally, we want to say that if f is equal to 0, what kind of the 1 norm of f equal to 0. So that's essentially by definition, if and only if the integral of absolute value of f equal to 0. And in the last lecture, we saw that the integral of a non-negative function is 0. That's if and only if this function is 0 almost everywhere. So that's if and only if the absolute value of f is equal to 0 almost everywhere mu. Well, that's really the same thing as saying f is equal to 0 almost everywhere mu. Okay, so we prove the last property. And I also want to do one more thing in this video. So we want to prove the following inequality. Is really useful later on. So the integral of an f, I'm really doing the integral of a real value function. So f can take negative value. All right, so this one is going to be less than or equals to the integral of the absolute value of f, which if you want, you can write it as the 1 norm of f, okay? So the proof, again, is we kind of already saw it. So we break f as f the positive part minus the f the negative part. And we saw that the f plus the f minus, their sum is just the absolute value of f, okay? So now this is just really just writing out the definition. So by definition, this real value function f, the integral is the difference between the integral of its positive part and the integral of its negative part. And no matter what, because f plus f minus are both non-negative, so this is going to be less than or equals to, I add these two up. All right, and this is just no other than the integral of their sum, which is the absolute value of f. Okay, and this by definition is the 1 norm of f. Okay, so now we prove this last proposition.